Apparently my resolution's too low. They're probably right. I don't know what resolution they want though. I feel like if I do 4K my computer will explode. But 480p is too low apparently. Makes sense, I guess. Alright, so welcome back to the stream of streamness. So, what I've been doing over these last few episodes, that is a good question. So, we've created a lot of files, but the main ones are here. The Python ones we've done. I would give an overview, but I haven't got all the image files to explain. The basic idea is you have a collection of points, you connect them up with different numbers, and we're doing like math/computer science manipulation with those numbers and stuff. Did I remember to put my microphone up? I did. Is that too high? I have no idea. There's no way I can get any feedback on that. Okay. This is the playlist if you haven't seen episodes 1 through 3. You can see that if you want. If not, in this episode it's mostly just computer science. So episode 1 was like all maths. Episodes 2 and 3 were a bit of maths, bit of computer science. And this one's going to be pretty much only computer science, doing all the technical details to finish off the algorithm. This is the long link if you don't like shortened links, but shortened link better. So there it is. Okay, I can save RAM by closing this. Why have I never done this before? Lol. There we go. Okay, so now to try and figure out how I connect this to episode 3 as best as possible. So episodes 1 and 2 and 3, I think it was 1, 2 and 3, we wrote this script which does everything we need to do for this series, Prim's algorithm in Python 3. Then we optimized it here. We've got a much shorter, more condensed algorithm that runs like the same speed and does everything the same. And today we're just finishing it off. So at the moment, there's no input, so you run it. Wait, is it not even... It's not running. Why is it not running? Is it just being slow? Probably being slow. We print total though. That's no fun. Done something wrong. Oh, there we go. So prints out 15, which we need. That's the answer to whatever matrix we input here. But at the moment it's a bit messy because we have to put the matrix in as this data structure thing. So because inputting it like this and typing it all out would just take too long, we created a script to fix this. We'll get matrix elements here. In today's episode we're going to be trying to improve it, I guess. Easier said than done. But before we do that, another thing I was talking about is with this algorithm, it gives out a list of the nodes that would represent the tree. So these 4 things should be outputted by the program. So you could use them to construct this minimum spanning tree here. We spoke about episode 1, which is basically our solution. We're trying to get this red thing. If we get that, then we built the roads properly. Everything is good. So last episode I was like, that's a big problem. How am I going to do it? That turns out we can just add an extra thing on the end. So before it was free C, but now it's free CA. So we can use all 3 symbols to do a thing. So by using all 3 symbols, this gives us extra information to work with. So I've got to work with that information. Don't want to be printing that. Okay. So what I'm thinking is we'll just have an array of all the solutions, which is going to store these 4 solutions here. And then these are where solutions are going to be stored in the array, which can store data. And you know how an array works at this point, if you've been watching up to episode 4. Or if not, then you're probably computer science enough to know what array is, stores data or whatever. And we also need a variable for previous, reason being, and now it's going to be A. So what previous is it's what node we're on before. So, oh wait, does that work? It works, but it's irrelevant. Going to keep track of which iteration we're on here. I'm going to bring in this script again because I'm confused. I need to know what's going on. So on the 0th iteration, got these possibilities. First these possibilities, this. Yeah, that's actually super cool. Oh, I wish I could undo this crossing out of this. I might just redraw it. Oh, that's going to take a while. Why'd I have to scribble for it? I mean, I know I had to scribble for it, I just didn't save before I undid the scribbles, so now they're permanently there. Such is life. Oh well, again, if you're at episode 4, you probably have a pretty good idea what's going on. I could explain it and make it better. Oh, forget it, we're doing it. Gotta make sure that everything makes sense, so I have to redraw out the matrix sad times. Although then I'll just be explaining a lot of the stuff I've already explained, so maybe this isn't a good idea. Oh, this is taking me no time to draw, so it's whatever. It's whatever. Wish there was something I could do at the same time, there really isn't. So, just got to draw high quality content. 5, 3, 11 dash. To draw out some letters. Worst drawn B you'll ever see there. Okay, so the way Prim's algorithm works, which should be aware of by now. What it does is it constructs this tree, which is always going to be the one which has the sum of the least numbers. So here we sum 3, 2, 3, 5 because those are the numbers associated to those lines that are red. And that gives us a value of 13. That's the cheapest way you can connect all the circles, or nodes as they're called by fancy computer science people and mathematicians if you're in network theory land. Okay, so the way it works, you cross out a node, you can choose this as arbitrary, we're going to choose A because that's what we've been doing the whole time. And basically after doing that you look at all the things underneath the circled one, so here it's 2 and 5, so hence here. No, it's a different array. Oh, we input a different matrix. Well, but if this was this one, it would print out 2BA, and it print out 5ZA, but it's not the same matrix, that's why it's doing different things. Oh well, that was a bit of a fail. These things happen. Alright, let's comment that out. What am I doing? Okay, I'm figuring out the smallest one. Oh, I need the... Where's the diagram? Bruh. I don't... Test data. There it is. Oh, it'd be better if I had the correct... Oh well. These things happen. So, what's happening on the first one? The first one's going to be A to C, because we start on A. The lowest one's 3. Well, let's figure out what the solution will be here. That's important. We'll go blue, because I feel like it. So the first edge, slash arc, slash relation, slash... I think I've been calling them arcs, so I'll call it an arc. It's just the line that connects A and C. The first one's A and C. The next one is A and D. Because we start here, and we've just got one line, we have to find the connected one. Then we've got DZ here. Boop. And then DB. Okay. So how's this answer given? So here 3 is the smallest, so we've got A there and the C there. So element, we count from 0 in computer science. Well, in some languages, in Python you count from 0. So I'm going to count from 0. We've got 0 element here, first element here, second element here. So it's the second element plus the first element. Let me write that somewhere because that's important too. We'll go E for element. E element 2. What's the symbol for concatenation? I'm going to use this. I don't know what the symbol is. It's like a double stroke, I think. But then that looks like it's 11. Let's make it really big. Concatenation element 1. So what we're saying is we're going to bring together and concatenate A to C to construct ACR. What's the lowest here? 5 is the lowest, and it's AD. Yep. Again, just first plus second. So it's just first plus second. That's good. We got the info we need. Now let's implement it. Where do you want to add the solution? Let's do it right at the very end. Solutions.append. Where is it going? Where does the data go? Oh. So we input in the possibilities and it returns back the smallest and the target ID. We need smallest. What's target ID? Target ID is the first element because that's our initial thing that we had. So what do we call this other one? Target ID. It's gotten to the point where we're calling it other ID because is there a better way to implement that? I don't think so. We need to update this method, gosh. And the index associated oh, it's the column it's in. Oh, that's good. And the index of the column, it's So what can we call it? We can call it column ID. Well, that's more specific than other ID. It's still not great. What I'm saying is that, where's my new diagram? There it is. What I'm saying is that when we cross out and we go, oh, 2 is our target value, because it's the smallest of 2 and 5, we're saying 2 is our first piece of data, B is our, oh, why are we doing, oh, blue's fine. No, it's not. It's fine. We're saying 2 is our value because it's smaller. That's the first piece of information. The second piece of information is that we're now circling B, and the third piece of information is that it's in column A. So we're returning these 3 things. The computer's doing the thinking of this. This method represents the thinking of a human of going 2 or 5, and then this represents the return values of that method, of it returning the smallest value, which is just the value it's chosen, the target ID associated to it, so whatever's here, and then whichever column it's in. So it's going to return column ID. We don't need any more inputs, it's fine how it is. Yeah, we can just add it as a third thing here. Epic. Well, that was easy. So now it's got the column ID. That's cool. Now what? Second here, first here. We've actually already done the thinking here. Where's my thinking? Here's my thinking. We're concatenating the second to the first. So we're concatenating column ID to target ID. That makes sense. We're going from that makes a lot of sense. At least the answer makes sense. Getting to it, less sense, but that's okay. Sometimes you just need an answer. Other times you need a solution too, but not right now. Engineering, you tend to require a solution less. That's more mathematics. Engineering, you just need it to work and then move on with your life. So what we're saying is saying this is representing where we're coming from, this is representing where we're going to. So going A, B, only we implemented A later, so that's why it's the second rather than the first. That's right, it's just the way around. But that is fine because we've named them anyway. So yeah, column ID to target ID. Column ID to target ID B. Dot append. Bro, we're basically done. Let's call it a solution. I'll call it solution arc. By solution arc, we just mean this thing. Let's hope that works. Boom. You know what, we can be really fancy here. This is very Python specific. You don't do this in other languages, but in Python you do, so we're going to do it. I will explain this code, but it's very unimportant. All it is putting them in a row like this. Oh, but now it's stepping. Oh, gross. That is a problem. No. Oh, it's just making it look pretty, but what other ways could I solve this problem? Oh. Really, we want solution output as a variable, and then we want to add them one by one. Can't decide if this solution is gross or a good idea. I'll explain after I've coded because that tends to work, I think. Then we're going to need a boundary here. I'm not sure what the boundary is yet, so we'll just do that for now. Oh, we should put a not. Just put a not. Not I smaller than solution range. No, it is well. If I is smaller than solution range, solution output plus equals comma space. Let's look at this monstrosity of code, what it does. Okay, that's not bad. So now I just need to figure out how to make it logic so it doesn't put that there. When does it put that there? It puts that there when I is equal to 1 less than solution len. When it's 1 less than solution len. 1 less than. Let's just try values. I can't be bothered. That works. Why does it work? I'm really not sure. But as I said before, at this point it's just make it work. It's good code. It's good code. I have no idea why it works, but it just is. Like, it's very clear to read, so. And it's imperative programming, so you can get away with these things. I don't know how declarative programming works, but I know it's more precise than this, where you just set up steps and it works and it's great. Okay, so what we're saying here is we're saying, well, you can read the code, but if you can't, I'll go through it. So what we're doing is we're saying solution output is nothing, and we're storing it in a word, in a variable called solution output. We're storing the length of the solution in here by using this method. Just returns the length of the array solution, which we've put stuff in throughout the algorithm. Every time it hits this code, it repeats 4 times because we told it to. And then what it does is we repeat for the length of the solution. That's what this means. This code, which is we're going to add one of the solutions, and then we're going to add a comma if I is within the bounds of this. Which all I did is basically I just tried values until I found that it works properly. But the code's there and you can read it if you want. And yeah. So we did it. We got a solution, we got the length of the solution. So we're saying how you construct the thing so that it connects it cheap as possible, and we say what the price is of connecting them. Now what? I have a to-do list somewhere. Oh, to-do list time. So we've got printing out the solution tree also. It's my first thing on here. The other 2 things are clean up the code, and we want an input script. I was planning on cleaning up the code first, and I still will. So what I mean by clean up the code is the code's pretty clean. Down here it's definitely good. We can delete these, because no, you know what, we'll leave it till the very, very end. Then right at the very end we'll delete it. Oh, and this is just a note telling me how to do it, but I remembered, so, oh wait. One of those is, the heck? What have I done? I think I want that there still. Let's do that. So here we got our functions and procedures, but seeing as these are abstractions, we could ditch them in a Python file. So that's the goal now. So I'm going to copy and paste. Now, I did do this before. Why did I do this before? No! In a Python file called functions and procedures, a well-named Python file called that. We've actually updated the code a bit, so we're going to put it in again. These are our functions and procedures. Now what we did before, these in the same directory. This one's in desktop/prims. This one's in desktop/prims. But they're not anymore because I moved them. Eh? They're here. What gives? I don't understand. I'm just going to leave it. They're in the same directory, so we can just import them. So what I tried to do before is, now that we've got it over there, the idea is we can delete this because it's saved somewhere else. Now we can just import it. So what we were trying before, we were just trying a simple import. Wait, how do these functions know about the constants? Because we imported them? I have no idea. I'm not going to look into that too much because that's confusing the heck out of me. Basically, I thought I had to put the constants at the top, but the code ran fine without doing that. I don't know. I guess because we declared the I don't know. Oh yeah, because I didn't know that. I've learned something new there. It's not important though. Anyway, import them. Import all the methods. Disregard row. Can I put it on the next line? Let's not test the theory. Let's rewrite it. Disregard row. What's the other one? Choose best. This isn't. I'm writing code that isn't going to work sometimes, just to demonstrate that it won't work. So it wants the constant, but it doesn't have the constant. Oh no! What do we do? Answer. There are a few things you could do. We could put the constants in here. But I kind of like having the constants in here. So this is no longer main anymore. This just is main. We don't need to put main anymore because we're cleaning things up. So I like having these all at the top. So I'm going to leave them at the top. What we're going to do is we're going to find a way to import these constants straight into this thing. So the way we do that is this needs to be more complex. At the moment it's literally just a list of 4. But we need to make it its own entity so it can deal with being given constants from elsewhere. So we're going to set up as a class. Classes are just basically giant functions that do function stuff. They're not functions, they're collections of functions, but they sort of interact as if it's a single thing, even though it's multiple things. So what's the class called? Oh, we can just call it after the file name. Procedures. It's not inheriting from everything because we don't need to. Boop. Oh, I can do it for all of it at the same time. There we go. Now it's all inside of the class. We've got 4 functions of this class. Oh. I'm going to define our constructor here. A constructor is just a method that gets run when you create it. We're going to have to create an object of this class. Just how classes work. What things do we need? We need these constants. Big number, empty, disregard. Now we're going to set these up as attributes. This is really repetitive, but it is what it is. If you ever read someone else's code, like, you know, when you just get like someone else's code, you don't understand what's going on, but you just like look for it anyway. You'll often see stuff like this. You'll be like, why? The reason why you do this is just because the computer needs to know that these things are these things, and you just have to type them out. It looks kind of stupid, but it's what it is. Basically what we're saying is this is an input, and then we're saying that this is now belonging to this specific instance of the object we've instantiated. Object-oriented programming is pretty difficult to explain. That's why I have whole courses on them or whatever. But we'll just use it. I won't go into why it works too much because it's really difficult to explain. So we set up 3 attributes now, and now we use the attributes. We also need to make sure that the thing knows that it belongs to it. Even though we've indented it, so you're like, oh, so it should know, we still have to tell it that it belongs to the thing. That's pretty much what this does. It lets it know that it's a class method rather than just a static one that's in a program somewhere. So example here, for this function, it's static to this script prim version 6.py. So we don't need to put self or anything, we just define the function and we can call it from within. But this is a specific function that belongs to this class, so we have to tell it that, so we have to add that extra word there to say. It's the basic idea. There's more going on, slightly more going on, but not much more. We never use the only time we actually use the constant is here, that's fine. We use the constant in all caps, which makes it way easier now to see their constants. Okay, and other than that, it's like chill. So now, instead of importing all of them, they're with a collection of called functions and procedures, so we're going to import the collection. But the main reason we did it in a collection isn't so we can make it less code here, because it was fine before. The reason we're doing it is so that we can do this, so we can put in our constants straight into the program. So the constants can be declared here, but used in this program, because we can add them here. So what we do is, we f&p functions and procedures. It's going to be our object local to this program. It's going to be equal to an object of this. And then we can pass in our constants, which are declared right above this code. So using these constants here straight into this setting up of this class in this code, we're setting up an instance of it called f&p. So now everything should be in here. And now if we wanted to use any of the methods, how often do we use the methods? It's one use. We can either, there's 2 ways we can solve this problem. The problem is that now to use our method, so here we use the method disregard row, the new syntax is f&p.disregard row. Reason being, if we want to be really fancy, we could pass them. No, we're not going to be that fancy. That's just more confusing. Now this is the new syntax, but we've used this syntax because it wasn't previously imported from a giant function, class thing. So we could either change it to f&p dot for all of them, or we could redefine the functions relative to the new syntax. Which do I prefer? Not sure. Let me remind myself what's going on. Here we've got imports, matrix, constants. I want to put the matrix further down. I don't like it there. Setting up of the object. Where would be a good place to set up the functions though? I guess here. Constants, functions, matrix load, program. Yeah, that's neat. Makes sense. It makes sense. It makes sense. It's a lot of typing, but yeah, it's fine. Could make the syntax shorter. The annoying thing is we could make the syntax S, F, and P, but then you have that. Usually it's stupid to name it one thing, but then it makes it quicker to type. We're doing it. It's the dilemma. No, F and P is way more clear. We can replace. We'll replace later. It'll be good. I'll show you. Oh no, but capital F, it might be elsewhere. We need to use a very specific symbol. Oh, program problems. We're just doing F and P. Oh, we could even do it on one line. Let's do it. Oh, we're getting super fancy here. Wow. Look at this Python programming. Oh, too fancy. 100% over-engineered, but whatever. There's this one YouTuber who gets really mad about over-engineering. I wish I knew his YouTube name, I don't. But if he was watching this, he'd be like, no, stop, you finished the program, stop over-engineering the heck out of it. But this is cool. You know, this isn't even over-engineering, this is just good programming. I don't know. It's definitely long. Whether or not it's good or not, I don't know. I feel like it's a bit clearer. Maybe, I don't know. Oh, but we don't know if initial small list is going to be passed or not. Yeah, we can just... Hmm. Yeah, no, it's fine. I'm overthinking this. It's really not a big deal. It's got a lot of inputs, so let's open our second line like that. And then it's just straight in. There we go. So what have we done here? We've redefined the local variables as being the class variables. The local methods as class methods, so we can condense it into less code with the same result. Very cool. And now it's very modularized, so here are our functions and procedures. Cool. It should run the exact same way it did before. We're just basically neating up the code. Nope, it does not like it. Non-type object is not iterable. Now we try and figure out why it doesn't like us. Seems fine. But we're inputting a column. Oh no. Why is it not happy with us? Line 32. This line of code. Seems fine to me. Get column, return dictionary. Oh, I know. These are not procedures, they are functions. Classic error. It all works now. Was that a waste of time? No, it's very neat now. Okay, now we can work on actual code. That was just being pedantic for no reason, and also demonstrating why object-oriented programming can be useful. If you want over-engineered code, then objects for the win. And sometimes over-engineered code is just cool and worth doing because it's so cool. Sometimes. Like right now. So you can be like, wow, the code's so readable. Okay, we package the thing. The last thing to do, input script, which we can modularize now because we're modularizing everything at this point, which is good. It's way easier to figure out what the heck's going on when it's all modularized, which is why object-oriented programming can be like a blessing. Modularization. So the question is, where is our input script? We code an input script. I just don't know where I put the input script. So now I have to go on a hunt for it. Get matrix elements. Does this have my input script? What's S? This is that. That's that architecture of it. Where's my other architecture of it? Oh no. I have code for that somewhere. I don't want to retype it. Experiment 1. Oh, it's got to be it, hasn't it? We found it. This is the code we're looking for. Gonna just yeet it into another document. This is our new document, isn't it? Right, let's give it a name first because we're being very professional, good programmers now, as opposed to just scrapping around with scripting before. Because this is the computer science episode, as opposed to the maths one, where we were just programming very badly but doing a lot of good maths. Now we're doing no maths at all and a lot of hopefully okay / good programming. What am I typing? Oh, whatever this is called. I mean, I've called the other one gate matrix elements, but it's a good name. It doesn't exist in there anymore. Yeah, let's just do it. No. That's not good. We now have multiple edit windows open for it. Did I override my previous file? Eh? I think it's just trying to warn me that it's called the same thing but it's a different place. It must be a different place, right? Oh my goodness, so confusing. Yeah, they're in different... They're in the same place? Eh? But it's not anymore. Oh, the confusion. They're in different places now. Now they're in different places. You know what? Whatever. It worked. I don't know why. Again, computer science episode is more software engineering episode, if I'm being honest. Which is engineering, which means you just botch things together as opposed to understanding on an intellectual level why they work. No, you just throw it together and then you risk assess it at the end. What's happening? We can be really creative with this. Matrix element getter. So constructor. I don't know if we need a constructor, but it's here for now. What am I going to call this method? Call it main. Is that confusing? Nah. Where's the code to copy paste? It's called experiment, isn't it? Aha. Boop. No. Ideally, moment. That wasn't enough. I don't know why that happened. But we need to double indent. Nice. What's happening? Symbols equals these. Okay. I've never used a private method before, So let's try for the first time. Get symbols. So this is going to be our input script. So this is going to be a little interface at the start of the program that says what data you want to input. So at the moment the input's hard-coded, but we want it to be more fluid. So making it more fluid now, that's the idea. So first of all we need to get num of symbols. Yeah, that's fine. I'm not used to doing input statements. First time using input of the whole thing, because it's an interface now. Input what? I don't know how to make a good input. Number of nodes of the network. Do we want that on a new line? I want it on a new line. It'll look fancy and cool. This is the new line character, so instead of being read as plain text, it gets read as a new line. If you want to have it read as plain text, you can do that, but we don't. We want it to cause a new line. Okay, so that's going to give us an integer. Oh wow, I have to input cast. Wow, this feels so different to everything else we've done so far. So we're getting an integer of number of nodes of the network. Then we're doing for I in range number of symbols. Array of the symbols they're going to add. Now we need a print statement to say what's going on here. Print elements. We want matrix elements getter. Print enter a symbol to use for each node. That's going to look good. Semicolon, because I use semicolons sometimes and sometimes I don't. Good times. For I in range, this is just a fixed loop. This is weird. This is how you syntax fixed loop in Python. Like, the way in your head you'd think you'd syntax it is repeat 4, repeat 5, depending on times you want to repeat the next section. In Python you do it like this. And this is the number of times we're repeating for the number of symbols entered. So at the end of 3 symbols we repeat 3 times, so they can enter all 3. But now I is not what we want it to be. I can fix that. Fixed. Okay. What am I doing? If while user in for user input equals none. Oh no, but now it's going to think that's in the list when it's not. How can I ensure? Let's just test it. While not user input in symbols. Oh gosh. Oh, what's happening? How do I even test this code? I have to instantiate it. Getting matrix elements, just so I know what's happening here, from underscore matrix underscore elements import matrix elements getter. Okay, now we're going to instantiate it. Matrix elements getter equals capital M because it's a class, elements getter class instantiated, and now, ooh, now we get to find out if our private method is a private method or not. Why is the name's too long? Get matrix stuff. It really doesn't matter. We just need it to be. Oh, it's too long. Get mat stuff. There we go. That's acceptable length. Get mat stuff dot underscore get symbols. It's a procedure, so we can run it as a procedure. Did I type it correctly? Yo, that's very cool. It's private. I like it. Well, that's what you call epic software design. So what we have to do is call it from inside the program. Yo, I take back what I said about private methods one time in the past. They're actually cool. When I first heard about private methods and private attributes, because I use Python and I didn't really know it existed, I was like, that's a crazy idea. Why would that ever be useful? But now I'm like, that's cool. I'm realizing now it's good. It's all good. Go. What happens? What? It didn't run the method. That means it's so private even the program can't. Unless I just... Okay, it works. I don't know what happened. Number of symbols. That's not going to run anything because there's no code there. There is, but it's the definition rather than executable code. Oh. Oh. It ran. Okay, I was worried that it would say, oh, nothing, while this isn't in this, but because the thing is empty, it would say, oh yeah, nothing is in there. But it didn't, none doesn't count as nothing, it counts as something. None is not nothing, it's something. This is programming for you. Good times. If user input, if not, I like to put not before. Reason being in Python 2, if you put it here, if user input not in, like, I'll show you. You could syntax it if user input not in symbols, and that would work on Python 3, but on Python 2 it doesn't work. There's no reason why this should work. This is a very stupid way of coding it, but Python 3 is so lenient, it lets you code it this way, because if you think about it as a Boolean expression, this makes no sense, but in English it makes sense. It's like, if this is not in this. But English isn't programming, so the fact it works in English does not mean it should work in programming. This shouldn't, because it makes no sense programming-wise. But Python 3 is lenient, but Python 2 isn't, and sometimes I use Python 2. So just so I don't end up writing code like that in Python 2, I code it properly in Python 3 like that, so we don't have any problems if I switch to Python 3, basically. But on Python 3, if you really want, you can type it out as if it's English, and it works, and it's crazy. Basically, Python 3 is just the easiest thing to learn programming with. It's so good. You can write English pretty much and it works. It's crazy. If not that and that. Symbols dot append. User input. Boom. Elif. Do I want to put else? I want to make it clear and put else if. In symbols. So saying, what if they put something that's already in there? So basically we're asking them to put in nodes, and if they put in a symbol that's not in the list, we're like, okay, well, we'll add it as a new symbol. But if they put a symbol they've already used before, we need to put a message saying, symbol already being used for another node. That's fine. That's not going to run. But this will run. So if we say 5, If we can put anything here, because there's nothing yet. And now if we try and put A again, oh no, it iterated. Huh? That wasn't meant to happen. Oh no, we've put while that isn't in there. Oh, nightmare. Oh, we want to put while user input in symbols. Oh, goodness me. But now we need to say a symbol that's in there when there's nothing in there. Oh. That's okay. We can do that. But now we're going to have to get rid of -1 at the end. Oh. Amazing. It might not be as bad as I think. Oh, that's gross. Oh my goodness me. I just realized something clever I could have done. I could actually run the method inside this script. I didn't though. Oh well. Doesn't matter now. Oh no, but now, because we append it, it continues to run the loop. Oh, it's a logic nightmare. We're saying while user input in symbols, run this code. I've got an idea. We're running this code if we know we've broken the while loop, which means we can write it outside the while loop. Now we can have an error message within it like, oh, I might have just solved it. I hope so. Again, you just keep trying until it works. Yes. 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 It won't let us put A or B for 3 because we put it in for 1 and 2. Oh, it's marvelous. Oh, it's fantastic. Oh, it's so fantastic. Let's go. And now we just need to get rid of our logic constant. -1 we put in there just so we know. Reason why I put -1 is because it's an integer, and we know the user can't input an integer because we force it to be a string here. Input by default always returns a string. So because it always returns a string, we're only putting strings in, which means the integer won't ever be a user input, which is good. Symbols.pop is the syntax for it, I think. Let's try it. We're just getting rid of -1, which is the 0th element because we put it in there first. All right. Oh, this is so cool. This is the coolest episode. It's also the one that at least people are likely to understand what's going on. If that's okay. Programmers unite. 3 nodes ABC. Oh, and it deletes the -1. All works so well with so little effort. Let's go. And who said object-oriented programming isn't good? I mean, this isn't object-oriented programming, so I don't know why I said that. We're using object-oriented programming, but not right now. Oh, but everything's so much more fun inside objects. Oh wait, no. Yeah, no. Objects are cool. I like objects. Oh my goodness. And then we can just jump straight into this one. So instead of the symbols being hard-coded, we now write in the symbols. Now we say let's just try it. So now we can say number of nodes of the network. Oh, that was silly. Number of nodes of the network 2. Symbols to use A and B from A to A. Oh, it's a network of just 2 nodes. That's okay. E for empty. A to B. weight of 5. B to A, same one, so weight of 5. This one empty. This is our elements thing, and this is our main code being run, because we're running our subprogram within the main program here. This is just running get matrix stuff, but then after running the matrix stuff we run our main stuff. So that's what this is. Okay, so we've got the elements, but then we never use the elements. We have to use the elements. Fire, ground, earth, water, I don't know. I want to copy paste code. I can't be bothered to write new code, but then I don't think I ever wrote this code, but I must have written this code. Because this is the heart and soul of the program. But I really never wrote the... We get a list of elements, but now we need to add these elements. I guess we have to rewrite the code because I never did it. Gosh, that's confusing. Why did I never do it? I don't know. For symbol 1 in symbols. Is it rows by columns or columns by rows? It's rows by columns. I'm just going to have to take a stab in the dark at that. I'm having to think all the way back to like episode 1 or 2. But I'm pretty certain, because that's why we had to have a get column method. Because getting a column is quite difficult in a rows by columns. Architecture. No. Yeah. So the rows are stored first, and then the columns are stored. Rows by columns, rows by columns. Classic matrix stuff. Rows first, then columns. I did good things with this by accident. Current row equals for symbol 2 in symbols. Now we need a counter variable. We haven't got a counter. So set up a counter. I equals -1. It's going to be our counter. So the increment code is that. Super nice. So we're saying I increment by 1. Now what? So I increments by 1, which means we can iterate through our elements array, which is just an array, not a dictionary, just an array. So current row S2 equals, I want to do it all compact like that because I feel like it, elements I. So we're saying for symbol and symbols, because we know we've set it up in such a way it will work. Why does this work? Does it work? It must work. Does it work? How can I even test it? Can I be bothered to test it? I might want to test it logically, prove it logically rather than test it the way you test stuff. Systematically? I don't know. You just test stuff. There's, I don't know what adjective to use for that. What am I doing? For symbol and symbols. Set up the thing. Oh, now we need to assign it. Oh. Matrix equals like that. Matrix S1 equals current row. So now we're embedding the dictionary we've set up into our bigger dictionary. You can't do 2 dimensions at once for good reasons. Like there was an episode in the past where I tried to index with 2 dimensions at once and it didn't work. I was like, why doesn't it work? And then I thought about it and then I realized programming wise, there's no reason why you should be able to do that. So it's probably a good thing you can't, and you can't, so that's good. Now what? Print out elements, and then we can print out yeah. I could have put those two statements on one line, but I didn't. So now let's put in a real matrix, no, a real graph, real network. I found it eventually. So now we're going to try and input this network using our new software. Sounds good to me. How many nodes? 1, 2, 3, 4, 5. Enter the symbol to use for each node. Okay then. Symbol to use. A, B, C, D, and then we call a file on Z. A to A, empty, A to B, 2, A to C, empty, A to D, empty, A to C, 5. I remember now my technique is to look at which ones it connects to. So here it connects A, Z, D, so the rest are nothing. A, Z, D, D is 5, C is 3, C to A. Oh, C only goes Z and D. Z and D. 7, 3. D only goes Z, B, C. 5, 7, empty, 11, and Z goes to 4, goes to everything. Yeah, it goes to everything except itself. Okay, 5, 3, 3, 11, nothing. So here's our list of elements. Then here's our output. So it's going row, then columns A, B, C, D, Z. And this is going to be A to Z. Did we ask A to Z for this value? We did, we asked A to Z. I'm just going to say it works. I'm pretty certain it works. But it's gotten to a point where I just want to finish it, so proving it or testing it is just, I might do it in my spare time. I probably won't do it in my spare time. So I'm just going to say it works. If it doesn't, then someone let me know. But otherwise, I think it's fine. So left to do else if input equals E. Oh, we need our empty constant. So we do need initiator. Input that. We're going to use that constant we've set up here. Okay. So maybe I want a bit of text at the start to tell the user that. I could do it here. Whoa, what did I do there? I made the code quit appear out of nowhere. I'm not sure how I did it. Oh well. I wish I did, that was cool. I don't know. Print. Now enter the weight from each node to each of the other nodes. For if two nodes do not connect, enter the value E. That'll be fine. Great, and now everything should work. Oh, I'd have to type out the whole thing. No, I don't, because we can just do a mock-up one. It's not going to do anything. Save it, and we can run it. Enter the nodes of the network 2, A and B. These are just two nodes that don't connect ever. And there we go. Using the keyword empty instead now, and that's good because we need it to use the keyword empty. And that keyword empty can be whatever we want because it's all set with a constant. Good programming uses constants, and that's why we've used them to the bitter end. We're nearly done. Oh my goodness me. I'm in shock. I can't believe it. We've been on a long journey to go, but it's reaching its end. Return. Oh my goodness, is this it? That might be it. And now instead of matrix equals equals our method. Oh my goodness. Is that it? Oh, now here, instead of saying, how do I get the first element of a matrix? After all this, the simplest of problems remains. So if we have a dictionary like this, how do I say I want the first element of A? Oh gosh. We're gonna have to look at the dictionary documentation. Okay, what about, okay, A is our dictionary, isn't it? A dot keys. A dot keys 0. No, does not support indexing. What do you support then? What a weird object then. Why doesn't it support indexing? It's literally just an array. I'm going to cast it and then do it again. Aha! We have an entry point, guys. Why is this important? Because here we need to know what the first key element is. And this code works, apparently. Which was a huge bodge that we managed to get this to work. We're not... we're going to set it up, and I was just going to directly put it in there, but it's just too complex. I'll just start node equals list of matrix dot keys 0. Now we'll start node matrix. No, did I delete my? Oh, I deleted my matrix. I can get a matrix. Where can I get a matrix from? I'll get a matrix in a second. It's so cool that we're now passing around a matrix as a data structure. Oh my goodness, this is cool. We can put these on 2 lines of code now. Things are getting a bit more complex here now. Start node. So we're disregarding the row node of the start node. Disregarding the row of the start node. And then we're putting the start node as a target ID because we need one target ID to begin the algorithm. And now we just need to find a matrix. There's a matrix here. Here it is. Copy that whole line. So we can get a matrix from our new method, but we also, just for now, for test data, we can also put in a matrix. Please work. And it works. Which means our program is done, pretty much. Oh my goodness. Which means, wait, let's clean up the code. No, let's run it first. No, I want to clean up the code first. No, I want to make sure it works first. Number of nodes, let's say we've got a hypothetical one of 2 of A and B. They don't connect there, but they connect there with the edge of 5. Okay. Something didn't work. Doesn't like it. Why not? Did it because we forgot to save it so it never returned our object? I don't know. Let's hope that was all the only problem was. Empty. 5, 5, empty. Oh boy. Is it because it's so small we're causing problems? But it should work. I guess I should put in a real data set. But we did put in a real data set and it worked. Where's our real data set? And why did I delete that code? I guess I was so confident it would work and it didn't. The real data set works, doesn't it? So why doesn't our inputted data set work? Let's see what's going on. We'll print out matrix. Whoa. It's because I didn't input an integer. I'm fine for it to break if you don't put in an integer. It could be a bit neater, but it's honestly fine. So we disregard A, and then it will have A as a target ID. Do we never set up target IDs? Ah, no we do. Target IDs equals empty row. So we should be able to append to it. Reference before assignment. And choose best. Let's see where it broke first. Line 48. It doesn't like the choose best method is freaking out. Let's go find out why the choose best method is not having a good time. That's in our functions and procedures module. Didn't like it. Why didn't you like it? Target ID reference before assignment. I'd say this is assignment. So I don't understand your problem, computer. Probably just because I inputted data too small. It's going to disregard A. It's going to look inside the A column, which will give us a value of 5. So it should say 5 for E impossibility. This all works for reference passing it in. Something's up though. E0 is smaller than smallest. Smallest equals target ID equals. And then we return the target ID, which we set up here. Column ID equals whatever the column it's in. Seems fine to me. Oh, we're looking at E, the second of E. The possibilities are set up such that the second one exists. Target ID and target IDs. Yeah, so that just means which column are we in. That should be fine. I don't see the problem. It's clearly a problem though. Local variable target ID reference before assignment. Oh dear. When you see the word local, you know things have gone pear-shaped. I think. It's running return before it's running any of this code. We can help debug by printing P. It's annoying I have to type this every time. I should probably just find a way to not have to type it every time. And I can do that by just not calling the method, so I should do that. It's being sent in an empty array. It doesn't know when to stop. Oh, we found our problem, guys. There is the problem. Staring us right in the face. It's a hard-coded number. Always going to be a problem. You don't want to be seeing those hard-coded numbers unless it's just, it makes sense like here, but this doesn't. It's just the number 4 for no reason. It's completely arbitrary. That's not good. Let's fix it. What we need to do is inside here, we need to return the number of symbols. I'm going to say symbols number of symbols equals number of nodes, and then we'll return matrix number of nodes. And then over here we'll save that. Important you save modules, I'm realizing now. I don't usually use this many modules. It's really good though, I really like it. It feels really nice. Now here we'll get matrix number of nodes. I can call this, I was going to say what it's called, but I can call it anyway here because we're in a different scope. Number of nodes, matrix number of nodes, number of nodes. But then we didn't do number of nodes, number of nodes minus 1. Okay, number of nodes minus 1 then. Take that. Did it work? Is there a chance of it breaking? Oh no, I have no idea. I'll have to think about this really hard afterwards. Nice. Minimum spanning tree is just A to B. Very cool. But will it always work? As long as it's connected, as long as we input a connected network, that should work. What's a connected network, you ask? It's a network that can be defined as you can get from any node to any other node. So this one's connected because if I choose any two nodes, so say I choose A and D, there is a way to get from A to D following paths. Sorry, following arcs that connect them. And you can do that for any connection of any set, any two nodes of the network. You can choose them and you'll be able to find a way to get from one to the other. It's an example of a network that's not connected. So if we did like this. So if we passed in this, it wouldn't work. Or if we passed in this and we had a third node C, it wouldn't work. But as long as everything's connected, so that would work, or that would work, then it will work. Network theory. Coming in again. Actually, I'm going to leave that. Why don't I leave that? Yeah. Network theory coming in hot. So that's it then. The code works. Alright, let's clean up the code then. Clean up the code and then it's done. And we can practice with something. Not practice, we can test it. Okay. So we might as well import this where we import everything else. We'll set up we'll call it its long name now because we can. I'm going to leave that in the final thing because it's an example of you can put the matrix straight in here. So I'll leave it. It's a useful comment. What's cool is that I don't even think I need to put any comments because it's all so readable. Oh, we make a matrix here. No reason to make a matrix there. Imports constants, I think that's the correct order to do stuff. Instantiate objects, use the object instantiation to make some local methods relative to our object. Instantiate a new thing, matrix elements getter. We're passing an empty because it needs that constant. Same reason we pass in these because it needs those constants. Then we get a matrix, we get the number of nodes of the matrix, that's important. Why is it important? Because Why is that important? I'm going to put in a comment on what this is. Example of a hard-coded matrix. If you wanted to hard-code matrix into this algorithm. Example of the hard-coded matrix format. If you wanted to hard-code a matrix into this algorithm. That's good, now it's clear. Total equals 0, target ID is equals an empty array. Our start node equals the first key element of the matrix. This code looks messy, but it works. It's not messy, it's cool. I don't know if there's a better way to do it, but that's a way to do it. It's not important that I do it the best way there. Because it's one line of code and speed is fine. Disregard row of the start node. Target ID append start node. Solution equals. Solution equals, oh, that's our solution. I should put that. This array will store the arcs of the solution. I should put a comment at the stop saying that this is. No, I don't. I don't need to put that because. Do I need to? I'll put it. Prim's algorithm in Python 3. Cool. What's this? It's a debug line. We don't need it anymore. I could put here possibility 0. What's possibility 0? For possibility in, possibilities equals, where do we set up a possibility? Oh, in the strip column. Strip column, get column, format. Element value. Matrix. Put that there. Element value, matrix column. Is it matrix row index? Matrix row index. Possibilities. Oh, that was quite nice actually. Element value, matrix row index, matrix column index. Is that right? You can print the possibility to find out. Well, I'm pretty certain on that. Matrix column index. Yeah, like we were saying, it's this one first. Why is it that one first? Oh, because that's what I thought was mostly. Yeah, they are most closely related. Because we're going down and then we're saying, oh, how are they related? Well, B with 2, and then we're saying column index. And that's quite good that we got row, column. It accidentally ended up being really good and clean. Smallest target ID, column ID. Total plus equals smallest. Disregard row, target ID matrix. Target ID is append target ID. Solutions append column ID plus target ID. This here at the start. Yeah. And then that's doing that thing. That's it. Bro, we have ourselves an algorithm. Nice and condensed. How many lines? Oh, that's what we like to see. Like 71 lines of code in the boilerplate, which is very cool. And then, what's happening here? Oh, that's some outdated version. Just chill. It's good. It's what allowed us to get where we are now. And then we've got module 1, matrix element getter. As we said, this is the thing that allows us to input the matrix. E works fine. It's not clear why it's E when you're inputting stuff, but it doesn't matter because when you come in and look inside, you can figure out why. Or if not, if you're not looking inside, you don't need to know why. You just type the letter E. And then functions and procedures. Yeah. I don't need a comment. It's self-explanatory. And again, I don't need a comment. It's self-explanatory. That's really it, isn't it? I could put a comment inside, but I really can't be bothered. These ones were cool because I was using them in the program. But in terms of giving the class, because you could do the same, you could put, this does a thing. You'd be able to access it quickly, so you could find out what it does quickly, but who cares? We don't need that anymore. It's finished. And it's self-explanatory. It's really well-written code, I think. This is pretty good. Doesn't look too nice, but that's mostly because the colors of IDLE is just awful. In terms of the code itself, it's pretty good. Maybe putting this inside a thing is messy, but I can't like it. Wow, I can't believe I'm actually at the end of this series. This series was epic. 4 episodes is a good number as well. I wonder how long this episode is. I can find out. Oh, not too long. An hour 30. We've reached the end. I don't know what. I feel like I should say something here, like closing thoughts or whatever. I don't know what to call it. Oh, I guess we should package it into a thing. How am I going to package it? So I'm going to make a folder called construction process, where we put all our working files in it. Boop. All right. Now we're going to make a new folder called Prim's algorithm, Python 3. Yeet. And then we're going to find the modules we need. Where are these stored? Desktop prims, functions and procedures. Here it is. Is this the code? Yeah. No, I can't. It's okay. Yeah. So where is it? Now we're going to get Prim version 6. Rename it main.py. So main.py is a way of saying this is the file to run. And these files won't run. Now there's also a thing you can do where you can make it only runnable from inside itself, but I'm not fancy enough to know how to do that. So we're not going to be doing that. That's Python itself. Let's make a new, can we start a shell? Oh, I didn't quite do what we wanted. Okay. Come on, main.py. Oh, one last thing, bother. I forgot to talk about this. I was going to do this, yeah, okay. It's just as well we tried to package everything and finish it. Okay. The big number. Oh, bother. Oh, that completely changes everything. Oh, not too much. That's annoying. Oh, you know when you like, you know when you got like homework or whatever, and you do the homework and you think it's done, and then you're like, oh, there's one last thing. It's basically what this is. You're like, oh, the software's done. We can package it, distribute it, and then you're like, oh, actually, that's not going to work. Okay. Here's what we're going to do. We're making a copy in case I mess everything up horrifically, which could easily happen. Now, so big number doesn't come into play until after we've got the matrix. So instead of doing it like that, we want to get the matrix first. There's more work to be done. Sad times. One out here too. So now we can make a proper big number. So big number, I just put 99999 to start with. But now we can make it more proper. So let's do that. This episode is going to be kind of long, but that's okay, because we're finishing everything off. And this is a mainly software engineering episode, which means it's mostly if you're into that kind of stuff, so being long is fine. So we got the matrix here. Now what we also want, in addition to these things, we want biggest value. Right, now let's go into the matrix getter. Why don't it let me copy? Oh, it did copy, but I haven't pasted it. Just so I can remember which is which. Okay, so let's open that and let's figure out how we fix this mess. Not mess thing. Okay. So we get the symbols. It's actually really well written. It's crazy considering how tired I was at the start that I've written this. Guess I've just had to do so many scripts for different things that it's starting to become intuitive. That's scary. That's not normal or okay. But I don't mind. It's a useful skill, I guess. What am I doing? Oh, if user input dot is digit. Aha. Biggest equals. What question do I ask? Enter the weights from each node to each of the other nodes. Yeah, you're not going to be entering negative numbers. If you do, you'll break my script, and that's okay, because you were silly enough to input negative numbers. Biggest equals -1. That's just we know -1 is going to be smaller than any possible number. We could put any number. We could put -20 if you want. -1 looks cool, and it's smaller than 0, so we know it'll be the smallest. We want to start with the smallest so we can put the biggest in there. So we say if user input into user input, it's a string, but we know it's going to be able to be casted to integer because we know user in.id digit is true, which means we know it's a digit, which means we know we can cast it to integer. Int user input bigger than biggest equals int user input. Boom. Return that biggest. Now we can do a really fancy thing. This is going to be so fancy. Are you ready for this? Main. This is our backup. Main copy is our working on biggest value. So now we can our big number constant can be equal to our biggest value of the matrix plus 1. So we know our constant big number will always be bigger than all the values in the matrix, because we know the biggest value, we just add 1, so now we know it's going to be the biggest number. And this is so much better than writing out 99999, because although that works if you only input small numbers... Oh, why'd I close the main? I'm a silly boy. Open that. Yeah. So, here we written 99999. But let's say, like, this isn't completely unreasonable. Let's say when we're running the script, like, oh, I've got a viewer, hello, welcome to the stream, doing coding stuff. So let's say we needed a network of 5 nodes. We'll give symbols A, B, C, D, E, yeah. And let's say the node from A to D was actually just a giant weight for some reason. Let's say it was this big. Well, now our edge weight is bigger than the limit of our program. And what that's going to do is it's going to cause massive errors, because we're relying on the fact this big number is the biggest number for the logic to work. So if you input a number that's bigger than our biggest number, bad things are going to happen. But by using our new method, our much more refined and better method, what we do is we find out what the biggest value is and add 1. So it means even if you add a huge number like this, we know our constant big number will always be bigger than any number you add, because our logic adds 1 to whatever you've added as your biggest number. So that's just a nice way that we can make sure the program can't be crashed from big numbers, which is good. A lot of video game exploits rely on that, where the computer has logic as if you can't have a value bigger than a certain value outside a certain boundary, and you do something within the video game to get a value outside those boundaries, you can break video games a lot of the time. That's how a lot of video game exploits work. But we don't want that. You don't like with video games, it's like whatever. But with scripts that do stuff like Prim's algorithm, you don't want there to be exploits. So we've covered our backs here. Now we make sure the big number is always the biggest number, which is good. So now we've got these two constants here. Oh, got these two constants here. Our final constant here. We can put all 3 constants into this to set up our functions. And now this is irrelevant. We don't need the default value of 99999, because we're always going to pass in our big number variable constant. And that's important that we pass in our big number, which we know is always going to be the biggest number, as opposed to defaulting to 99999. That's not good. It works for testing phase, but we need to move out of it for final phase. And fortunately, that didn't take too long to implement. That was a really quick implementation. And now we can package everything like we were doing before. It's all done now. Oh yeah. So, yeah, here's our biggest code now in there too. Did we make sure it worked? I haven't made sure it works. I should I should make sure it worked. My one view, if you have any questions, do feel free to post something, or just say hi or whatever. Unless you're not logged, signed in or whatever. However YouTube works. I don't know how YouTube works. YouTube's confusing. I'm going to print the biggest value just to make sure our code actually works, and I haven't done a dumb. So if we set up a matrix of... No. How many nodes do I want? 4 nodes be okay? Or maybe I do want 5 nodes, I'm dumb. A to A, nothing. A to B. Right, so we'll go 4, 7, 3, 18. So we're expecting 9. Bother. What? This index out of range? I think it just broke because I gave it EE. Oh, but that should be fine. What did I do? Oh no. Oh no, something doesn't work. Yeah, this is the problem. It's because we didn't put E. There's no problems here. It's just we didn't type E, so it broke. As we told it to. So, no surprises really. 5. What did we do before as test data? So 22 is our biggest value now. Got to be careful, make sure it's only 1e. Oh, it's breaking the program, but it's okay, I didn't break it. Biggest value of 22, which means our big number variable will be 23. It's bigger than all the elements. Our code works. Good. It all works. That's all we needed to know. And now we can get back to trying to package it or whatever. This is our updated code. We got biggest, we got biggest. We return biggest at the bottom, do we? Ooh. Yeah. In here, we didn't change anything here. It might be, it looks like a problem that we got a default value, but it really doesn't matter because we are always going to pass a value, so it doesn't matter that we've got a default setup. We can leave it. Alright, let's put this in the construction process folder. This PyCache folder is important. It does good things, I think. I don't really understand how it works, so you just leave it, I think. I'll just rename this main, and I think we're done. That's it. Prim's algorithm in Python 3. Oh. Constant, 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 loads at the top. Comment to say what it does. Can make it like that if we really want, it doesn't really matter. Example of hard coding it. Comment that makes sense. Comment so people can understand even if they haven't a clue what's going on. Well, this is just, there's lots of things I don't explain. This is a very weird thing that I choose to explain, but whatever. Maybe I want it there. No, I like it there. Yeah, that's fine. And this is saying what this is because it's not clear immediately. But then output those two things. And then just some white space at the end just because. And then got our things. What happens if I delete that? It still runs fine, doesn't it? So I guess I can distribute it without the PyCache folder. Oh, there we go. Yeah, I should probably test it works and stuff. Okay, so I guess the final stage of the software development of this algorithm, Prim's algorithm in Python 3 by jumpre, is just give it some test data, so that's what we're going to do. So let's set up a matrix. Oh, I've not got any viewers. I do, but they're not commenting. Okay, that's fair. Probably not signed in. Subtimes. Oh well. So I guess I'll just choose some numbers. Just draw a network. So now we've got a computer, and we can go loads of nodes. Like usually you'd be limited to number of nodes, but not so much here. Although it does ask us the same question twice, which means it takes us longer than it might do if you had a better input system than I do, but that's fine. I'm going to label them too. A, B, C, D. It might be nice if you could input them yourself as opposed to it asking you questions, but it's fine. G, H. I was going to say, oh no, what if they enter nothing as the symbol for the node, but that's actually fine, my program can deal with that, because an empty string is still a unique string, and I only use strings as keys over anything else, so it really doesn't matter. That's pretty sick. Oh, this is way too much fun. There we go, let's enter some values. 3, 2. 5, 17, 8, 6, 3. It's getting confusing which number's assigned to which one. 5, 2, we've got 8 going there. Oh no, what a mess. I should do like a blue mark or whatever for ones I've, yeah, it's not blue. So that one's done, that one's done. That one's got 3, 5, 2. What's that 3 responding to? I think it's responding to one that's already been done. So that's fun. Oh dear. Oh dear. It's falling apart. There we go. Done 5, 2. Oh, it's so hard to figure out which ones I've done and which ones I haven't. Software engineering fail. 3, 6, 17, 12. Let's do a really big one just for no reason at all. 99. Which nodes haven't we done? Meant arcs. 2's been done. Have we done all of them? We finally made it, squad. Took about 1,000,000 years, but there we go. We have the final challenge for our program. Well, not the final challenge, just testing to show our program works. Let's input it. How many nodes has it got? It goes up to H, which means it's got 8 nodes. Enter a symbol of each node. A does not connect to A. A connects to B. No, it doesn't. What does it connect to? It connects to C and F. C with a weight of 8. And F with a node. It's annoying you can't do, actually. That's something to consider. But hopefully we just won't make any mistakes. B connects to H, G, E. HG, so it connects to the E with a weight of 2. No, it doesn't print out the matrix. Oh no, that is something to add. This is why you test stuff, I guess, to make sure you figure out stuff that would be useful. Bother it, that is annoying. Oh no, it's fine. We can access it at the end. It's fine. Overthinking it. G and E, H, G and E, G, 5, H3, C to A, or goes to lots of different things. This one doesn't go to B though, does not go to itself. 12, C to E, doesn't go to E, C to F, 99, C to G, does it go to G? It doesn't go to G, it does go to H, 6, D to A. It'd be way quicker to do this in person than a computer. Oh my goodness. So I'm guessing there's times when being able to do it in a computer is useful, but here it's like C and E. I guess it's more of a proof of concept than anything else then. Well, as far as I'm concerned. E to B, 2. E to D, E to F, 6. Doesn't go to G or to H. Oh, this is taking so long. Why? It's quite fast though, considering how easy it was to program. It's not perfect, but it's pretty good. Do we do 4 for F? 1, 2, 3, yeah. G to A, G to B. Only goes to B and F. Okay. H to A, it doesn't go to A, it only goes to B and C. That's good. To B with a weight of 3. To C with a weight of 6. Oh, we're nearly done, guys. What's the solution? Oops, it's not meant to print those things out. That's another problem. There's our solution. A, C, C, H, H, B, B, E, B, G, G, F, C, D. Cool. The weight of 39. We can test it if we want, but I trust the algorithm. Oh wait, this is test data. We actually meant to test it. Okay, I guess. And then printing out all of this was a mistake. Oh well. And I realised my problem before was, oh no, but we can't see our matrix, but we can. This is the matrix. No, but it's been fully disregarded. That's pretty funny. Well, classic, really. Don't know why that's so funny to me. I guess it's like when you cross, it's just like, I don't know why I find that so funny. 8 is the smallest. What's connected that's smaller? Yo, doing this by hand is actually a pain. Never mind, the computer did good things. 12. And this is why you get a computer to do things, I guess. 'Cause doing it yourself is actually not fun. Wow. I'm just going to look at the solution. H to B. Oh, that's the next best one, is it? Or we could have done D to E. E was the solution. No, that's only 3. I forgot it was only 3. Gosh, the computer was actually really good. Never mind, it wasn't a complete waste of time, that was cool. Is that a solution? Yeah, everything's connected. And now let's put it in a calculator to find out. If we got the same value as the computer, 39. 8 plus 12 plus 2 plus 3 plus 6 plus 3. Maybe I didn't type it right. 8 plus 3 plus 6 plus 12 plus 2 plus 6 plus 3. 40. Am I putting something in wrong? Oh no. I keep getting different values each time. I need to figure out what's going on. Let me circle the correct ones. Let's use a colour we haven't used yet. Green. 8, 3, 6, 2. It's actually cool how it like cuts past all of the nonsense I put up there to find the most optimized route. It's actually pretty sick. How many values we got there? Quite a few. 3 plus 2 plus 8 plus 12 plus 6 plus 3 plus 6. 40. Computer's outputting 39. Oh no. What went wrong? A to C, C to H, C to H, oh yeah, C to H, H to B, yeah, we got that, B to E, yeah, B to G. We missed B to G. We did the algorithm wrong. We made a human error. Oh my goodness, the algorithm's so good it catches out on stuff you miss. Whoa, my mind is officially blown. That's crazy. I thought it was wrong, but it turns out I was wrong. Oh my goodness, this is why computers exist. Oh my goodness. That's crazy. 39. Yeah, there's some cleaning up to do though. There's this mess to figure out, and then it'd be quite nice if you could look up the matrix so you can hard code it back in at the end, because now I can't run the algorithm again. So that was kind of stupid. That's really easy to do though. Okay, let's fix it then. It's the old version. Oh, was I running the old version? No, I can't have been. I have no idea. Oh, I can find out what I executed. It has it in the stream. It tells us what we executed. We executed the correct one. That's cool. Okay. So why does it print out these things? There must be a print statement that we haven't commented out. But where? Could be in any of the modules. No, it couldn't. We didn't see any prints in the start bit, so it can't be in the start module. Where's the print statement? There it is. Bye bye. Okay, gone. Problem 1 fixed. Problem 2, that's fixable really easily. What we do is just here we put save of matrix equals matrix. No, equals a string of the matrix. So that way it'll save it. If we just said save a matrix equals matrix, it doesn't actually copy it. It copies the reference of the matrix because of the way Python works, which means that when we modify matrix, we'll modify the save of the matrix, which is really weird and hard to get used to, but that's how it is. But if we do a string, it'll work. It's actually good it does it that way for reasons I won't get into now because it's irrelevant right now. So what we want really is we want one more question. Yeah. And we want one more question inside that module that says user input equals input. Do you want of the matrix? No, we don't need to do this because do we need to or do we not? Let me show you what's happening. Gosh, this episode's really long, but whatever. It's fine. Oh. Fine, we'll delete that line of code. Now we can do save of matrix. We could do it at the end. We could say, do you want a hard-coded copy of the matrix? But then you can ask it for it by doing that. Decisions. How do I want to do it? Yeah, but no, the user can, if they want it to save a copy of the matrix, they can either do it themselves or realize that I've already done it and use that variable. The user will be able to figure it out, so the idea of them being able to choose is irrelevant. Well, not irrelevant, but yeah, irrelevant, not necessary. But I can get rid of that line of code. And it's done. That's all there is to it. Yeah. That's it. Gosh, project demolished. It's over. It's all done. So that's the end. So what am I going to do with this software? So this is our software here. Oh, I've closed Python now. Okay, that's fine. Here's the software here. And you can run the main and you can do Prim's algorithm. And it's the whole of Prim's algorithm in Python 3 with these two modules which you see in code. So what I'll do is at some point, hopefully soon after this video, if I don't feel like it then it'll be later. But at some point I'm going to put the source code here, a link to it in the description so you can have a look for it if you want. Maybe make suggestions and show me. I've got a Discord server. Cheers. Oh, where am I going to put it? You know what I'm going to do? I'm going to go into here, go boop, you can, it's, yeah, that colour works. I'm going to call it, wait for it to load, I'll call it canvas. Ah! It's been moved. Yeah, save it to wherever it's been moved to. Oh yeah, I put it in some other folder. I'm doing this also I can show my Discord server. Wow. Content. .ly/co/discord. There we go. That's the link. That's the URL to my Discord. So if you're on Discord, you can join. And then if you look for this, you know, like your code sucks, and you can point out how you can make it better, and you can tell me about it. Show me your code, see what you did differently. This is how I would solve doing Prim's algorithm in Python 3, as you see me go through this series. So yeah, it's Discord. This is the end of the series, I guess. Yay, I finished it. So let me just open all of them side by side because I can. Oh, actually, last thing I'm going to do, I'm going to change the order of these two lines because we've changed how it works with it, so it kind of makes more sense this way because we use this function first. It's a really small change. There we go. So there's our main. There's our matrix element getter, and there's our functions and procedures that make all the logic of the main heart of the program here work. So that's it. So I hope you guys, oh, I can do fun stuff, can't I? Whoa, I'm massive now. Okay, well, I hope you guys enjoyed that series. Let me know what you thought in the comment section if you want to see anything similar, different, any feedback or anything. I don't know. Do whatever. See you in a bit. I'll go back to this screen actually. So, see you guys later.